Welcome back to the lab. Today we are launching a mini-series. Not just any mini-series, we are launching a mini-series about comparators, and we are starting from square one, Ohm's Law. If you're new to electronics, then welcome. Let's build something great together. Let's build some knowledge, but before we dive in, I want to answer some questions you probably don't have. Who or what is Ohm, and why do they have a law, and what are we talking about? Well, let's lay some framework. Electronics and circuits all start with voltage, otherwise known as electromotive force. Voltage is electrical potential energy, much like gravitational potential energy, kinetic energy, and chemical potential energy. Voltage provides an opportunity to do some work. If we use a voltage source and we drive current through something like a motor, then real work can be done. Electrical energy is real energy that can do real work. Okay, great. So how do we know how much voltage we need? Well, when a voltage is applied across an impedance, current will flow. Let's pretend that everything is a simple, perfect resistor for now. This assumption will make a lot of math easy while we nail down the basics. If a voltage is applied across a resistance, a finite quantity of current will flow. This is where Ohm comes in. Georg Ohm, in fact. This Ohm guy did some research in 1825 and 1826 about how voltage, current, and resistance are related, and this is what he discovered. Voltage, measured in volts, is equal to the current flowing through a circuit in amperes, or amps, multiplied by the resistance, measured in ohms. There we go. Voltage equals current times resistance, or V equals I times R, the fundamental equation that relates voltage, current, and resistance. Awesome. It's at this point where we can really kick things off. We've established the basics of voltage, current, and resistance, so let's take this one step further. Fair warning, there's going to be a few assumptions that we're working with here. We will be assuming that all of our voltage sources are the same voltage, all of our resistances are the same resistance, and yeah, that's it. That's all we're assuming. So let's kick this off by considering three cases. Here we have a voltage source in volts, a current that is flowing through the circuit, and a resistor R1. Case 2, things are going to get a little more interesting here. Let's say we have two of those voltage sources. Let's call them batteries. Two of those sources in parallel, one resistance. Now, I might have been cheating a little bit with my dot notation, but that's okay. So, right, we were saying that each of these voltages is the same voltage. All of these resistors are the same resistance. What does that tell us about the currents? Well, Ohm's law V equals I times R, voltage equals current times resistance. You know, we might need to rearrange this. And I don't know about you, but I'm not very good at algebra, so let's pull the resistance over to that side of the equation. So we're left with I equals V divided by R. We had to divide both sides of this equation by resistance. Now, what does this tell us about I1, I2, and I3? Okay. Well, I1 is just equal to I1. It's just itself. It's kind of the baseline, right? One voltage, one current, one resistor. We're going to call that I1. What does that tell us about I2 then? Well, I2 has two voltage sources and one resistor. Voltage equals current times resistance. Current equals voltage divided by resistance. If the resistance stays the same and the voltage doubles, we don't really know what I1 was, but we know that I2 will be equal to 2 times I1, because the voltage 2 is twice the voltage 1. And then what does that say about current 3? Well, current 3 has 1 voltage and 2 resistors in series, so there's twice as much resistance in the circuit. Since series resistors add, there's twice as much resistance, the same amount of voltage, so that means that this must be equal to 1/2 I1. But we also know something else. Since I2 is equal to 2 times I1, and I3 is equal to 1/2 I1, we can also know that I3 is equal to 1/4 of I2. There's this relationship linking all of these situations because voltage, current, and resistance are all related so intimately. Okay, so where do we go from here? That's, a fairly good baseline, but there has to be another application of this, and not every circuit looks like one resistor, 2 resistors, or a couple voltage sources. So let's put some numbers in the situation to apply this to a real situation. Doing that, I think, will be a little more powerful. So let's start this off pretty easy. Don't want to hurt myself. So we're going to take this to be V1. It's going to be 1 volt. And we're going to add a resistor. We're going to make that 1 ohm with a current I1. Okay? This is where we're starting. Let's try to find I1. Well, if I'm being honest, by inspection, it's 1 amp. But why? Well, let's not forget voltage equals current times resistance. 1 volt, 1 ohm. So if we take a volt divided by an ohm, just like we did here, 1 divided by 1 is 1. That's the application of Ohm's Law. That one's pretty easy. Okay, let's try another one. We've got ourselves a voltage source. We've got ourselves a resistor. We're going to say that this is 10 volts and this is 1 ohm. And I might be letting my notation slip a little bit. Hopefully you can follow. Okay. R2, V2. Okay. In this case, I2 is equal to 10 amps. Now why 10 amps? Same reason as before, right? Ohm's Law. Voltage equals current times resistance. Current equals voltage divided by resistance. So if we take the voltage, 10 volts, we divide that by 1 ohm, you get 10. 10 divided by 1 is 10. Now, this was still pretty easy. I admit it's pretty basic, so let's step it up again. Let's make this a little bit harder. So now we have a V3. We're going to make this 5 volts. We're going to have an I3 that is equal to 0.1 amps. And we're going to have an R3 that is unknown. Ooh, now we're getting a little tricky. Okay, let's still try to solve this. Now, this isn't fundamentally a different problem. I think we can still use Ohm's Law to solve this. We might just need to flip it around a little bit. V equals I times R, that's the fundamental law. Let's flip this around for resistance. So that would be voltage over current equals resistance. Excellent. With that in mind, we then know that R3 is equal to 5 volts divided by 0.1 amp, which is 50 ohms. That means that in order for this to be 0.1 amp and this to be 5 volts, R3 must be equal to 50 ohms. Excellent. Now, before we graduate onto more complex circuits here, I just want to lay out a couple more fundamental things about circuits. Series and parallel combination. So for series connected resistors, let's say that we've got these two resistors in parallel, R1 and R2, and we want some kind of something. We want something, and we're going to call this Req. So let's say we replaced these two resistors with one bigger resistor. How do we know what Req should be? Well, for a series connected resistor, the equivalent resistance is simply R1 plus R2. Easy. For something like a parallel connected resistor, so then Req would be, right over here. It'd be these two together if you were to merge them into one. Now we've got two options. You can either say that Req is equal to 1 over R1 plus 1 over R2, or this one's great. Sorry, not or. This one's great because you can keep adding more resistors here if there's many in parallel. But if there's only two, and you know there's only two, you have another option. And that's Req equals R1 times R2 over R1 plus R2. And parentheses are going to be a trick if you're punching that into a calculator. Okay? So the reason why this works out, right, is we have ohms times ohms, so that'd be ohms squared divided by ohms, which brings you back into ohms. Where this one just is always ohms. It's either ohms or rho, or it's admittance or it's impedance, but you flip it twice, so you end up with ohms. So that's kind of fundamentally how you do series and parallel combination, and we're going to work that in with some numbers in just a second. Okay, the mad ramblings of an engineer. I love it. I love it. Let's keep this going. So we're going to do two examples here, and I'm going to try to keep them relatively simple. We're going to start with V1 equals 10 volts. I1 equals 0.004 amps, or 4 milliamps. We've got an R1 and an R2, where R1 is equal to 1000 ohms, or 1 kilo ohm, and R2 is unknown. Okay, now I'll put my work down below. So in this case, we want to apply the series equivalent resistance equation. Req series is equal to 10 volts divided by 0.004 amps, which is equal to 2500 ohms. So now we know that the total resistance must be 2500 ohms because we know that there is 4 milliamps flowing through R1 and R2, and there's 10 volts, right? We have a fixed voltage, we have a fixed current, we have a fixed resistance, and that fixed resistance must be 2500 ohms. Knowing how Req works, we know this is equal to R1 plus R2, so if we know that 2500 ohms is equal to 1000 ohms plus something, we know that that something is going to be equal to 1500 ohms. Take 2500, subtract 1000, there you go. And, just for fun, what's the voltage at this node? This is fundamentally voltage division, right? We're going to need to talk about this at some point in the future, or either at least allude to it, but voltage division is basically just what is the voltage at that node. Okay, well, we know how much current's flowing through it, right? We know there's 0.004 amps, 4 milliamps flowing through. Okay. And we know that it's 1500 ohms. There you go. 6 volts. So we know that there's 4 volts on R1, there's 4 volts on 4 volts on R1, 6 volts on R2, and 10 volts in total. We're dropping 10 volts over here, we're adding 10 volts over here. Our circuit is balanced. That means the math checks out. We'll get more on that when we get to nodal and mesh analysis, but for right now, we're just going to leave it at that. The voltage across the drops needs to be equal to the voltage across the sources. Okay. Now, let's look at a slightly more complex example. We still have one voltage source. Let's get that drawn in. But this time we're going to be solving for current. That's a question mark, not a 2. It looks just kind of like a scribble. Big question mark. There we go. R3 equals 4 ohms. R2 equals 2 ohms. Ooh, this circuit's even a little crooked. That's a feature. R3 equals 10 ohms. That's awesome. That's awesome. Would you believe me if I said I was good at coloring between the lines in elementary school? Probably not. That's okay though. So now we've got kind of two things here, right? What we really want to solve for is, if I just sketch this in, this is what we want. We want this equivalent resistor, but that involves both a series combination and a parallel combination. So that is not straightforward. How do we do this? Well, we can't directly apply our series formula, right? We can't say R3 equals R3 plus, no, it's R3 plus the equivalent resistance of these two. So let's start with the parallel combination to simplify this. So I could solve this either way, but I'm just going to use some standard notation just to make sure we're all familiar with it. So I'm going to say REQ parallel equals R3 in parallel with R2. That's a standard way to write that. It's like a double parallel bar. And I'll use the 2 resistor on the equation. So let's say that's 2 times 4 over 2 plus 4. 8 over 6, or 1 1/3 ohm. Okay. So now let's plug that in. Let's do our equivalent series resistance. So now we know that's REQ parallel plus 10 ohms, which is 11 1/3 ohm. Notice I'm not rounding yet. I'm keeping this in fractional form until we're at the end, because otherwise you'd recursively or continuously lose precision as you add things together, and it's better if you can leave it as a fraction. There's an amount of significant figures where the difference is negligible, but I'm saying better, right? As best practice, it's best to hold on to that until you're at the end. So then I1 is equal to V1 over REQ, this series resistor. Right, this is Ohm's Law again. This is familiar because we're solving for I1, right? V equals I times R, I equals V over R. Same story, just different application. And this is, the big REQ that we just solved for. Okay? That's the 11 1/3 ohms. So now we know that that's 5 volts divided by 11 1/3 ohms. 0.441 amps. Isn't that awesome? So what we just did is we just used Ohm's Law and a series and parallel combination formula to evaluate a relatively complex circuit situation, relatively complex scenario. I think that's pretty cool. that's really about all that we have time for today. I want to make sure that we're able to kind of walk through this at a reasonable pace and share things with you. But let me promise you that there is more coming. There is going to be more content like this on the way. I think that we laid a great framework for what's coming. Like, this is going to be instrumental, and this is a part of our larger series on comparator circuits where I want no assumptions going in, no prerequisite knowledge required. I want to take you from, what is voltage? That's where we started today. What is voltage? And get you through, a good bit through circuits 1 by the time we get to comparators. Obviously, we won't be able to touch all the nuances of current sources versus voltage sources. This isn't, a full education, but it's going to be pretty cool. There's going to be a lot of great information packed in here, and I'm really happy that you're here with us. So, throwback to circuits 1, yeah! If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. Coming up next, we'll expand this discussion into theory of superposition and evaluate more complex circuit networks. I'm pretty excited for this little series. If you want a copy of this engineering paper, not that there's really anything super special about it, but if you want a copy of it, there'll be a link to that. There's a PDF down below. And if you'd like to support the channel, consider checking out our Patreon page linked in the description. It really helps a lot. Thank you. Seriously, thank you to everyone who has decided to become a member. You are a big part of keeping this all possible, and every little bit helps. Thank you. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EEforEveryone, and thank you for staying till the end. Bye!